Continuing on with Unit 9, this is Learning Target 9B, Solving Quadratic Equations, Part 1. So in Learning Target 9B, we're going to learn how to solve quadratic equations using 3 different methods, and then in Learning Target 9C, we're going to continue learning other methods on how to solve quadratic equations. By the end of this video, you will be able to find the solutions to a quadratic equation by graphing, and also solve a quadratic equation by using square roots. So in our last video, we talked about what a quadratic function was, and we learned how to graph those functions from standard form. Now we're going to look at quadratic equations. A quadratic equation is an equation of the form ax squared plus bx plus c. So we're used to seeing this from our last video, but now this is going to be set equal to 0 because we're trying to solve for x. So instead of having y equals, I'm setting y equal to 0 and solving for our x. Again, we do have this little restriction that a cannot equal 0 because we want to make sure we have the x squared term. Now there are lots of ways to solve quadratic equations, and in Learning Target 9B, we're going to look at 3 ways. In this video, we're going to look at graphing and square roots. In our Part 2 of Learning Target 9B video, we're going to look at how to solve using the zero product property, which is also going to give us a nice refresher in factoring quadratic equations. The other thing I want to point out is graphing. You can use graphing anytime actually, but you only want to use it if it's a function that's easy or it's quick to graph. Square roots, on the other hand, only work if the b term is equal to 0. So remember that b term is our middle term with our x there, so square roots only work if that middle term is going to be equal to 0. Need a little bit of vocab before we move forward with our first set of examples. A solution for a quadratic equation has lots of names, and they all actually mean the same thing. So as you get onto an Algebra 2 class, you're going to see these words being used interchangeably a lot, but the reason we're going to talk about them now is so that we understand why the answer is on the graph that we're finding. So solutions, a couple other names for that would be roots, zeros, or x-intercepts, and I really want to talk about this x-intercepts portion. So solutions and x-intercepts mean the same thing, and the reason they do is, let's think about what an x-intercept is. An x-intercept is when we set y equal to 0. So if I start with a quadratic function, y equals ax squared plus bx plus c, then to find an x-intercept, I would set y to equal 0. So I'd get 0 equals ax squared plus bx plus c. Well, this is exactly what we're solving in a quadratic equation. So a quadratic equation is when I set y to 0, but that's the same thing as an x-intercept, which is why solutions and x-intercepts are actually the same thing. So on our graph then, when we're solving these by graphing, we're going to be looking for our x-intercepts. Let's look at our first example. So it says solve the following quadratic equations by graphing. And remember, when we're solving by graphing, we're looking for the x-intercepts. And I want to say that it could be more than one x-intercept. We know that a quadratic equation makes our parabola shape that either opens up or it could be opening down. As a refresher, how do I know if the parabola opens up versus if the parabola opens down? So the parabola opens up if our a value is bigger than 0, so that was our smiley face, and if our a value is less than 0, then the graph would be opening facing downward, that was our frowny face. And because of this, we could have more than one x-intercept, or we might have no x-intercepts, or we might only have one x-intercept. Our first example says x squared minus 1 equals 0. I'm going to change this back into the quadratic function, so we're instead going to graph y equals x squared minus 1. So I'm replacing the 0 with our y just so that I can be able to draw a t-chart and find some values here. So let's take the nicest value. The nicest value I could sub in would be 0. If I sub that in, we end up with 0 squared minus 1, so I end up with negative 1. So let's start plotting this on our graph. So I'm down here at 0, negative 1. For our next point, why don't I go ahead and sub in 1? We get 1 squared minus 1. Well, that's going to give us 0. So I have the coordinate pair 1, 0 then. Then let's see, so I know I should get some type of U shape. Because my A value here is positive, the graph should be facing up. So that means that it's got to curve somehow, but maybe it keeps curving down further, we're not sure. So let's find a point to the left of x equals 0. Let's use x equals -1. When we sub that in, we get -1 squared minus 1. Well, -1 squared is equal to +1, and then 1 minus 1 will give us 0 again. So I get another x-intercept that we found. What this is telling me then is that my U shape is, going through those points, so curving down and keeps going up, and then over here it curves down and keeps going up as well. Now in the last section I know we found 5 points, and we could keep finding more points on here. The reason I stopped is because I can already see where I have a vertex. I have my vertex here at 0, -1, and I found 2 x-intercepts. There's no way that I could have more than 2 x-intercepts if I'm going to have a U-shaped as my graph. The most x-intercepts I could have then would be 2. What this tells me then is since I have x-intercepts, there we go, at -1, 0, and 1, 0, then that tells me that my solutions then are going to be x equals -1 and x equals +1. And those will be our 2 answers. We could write our answers as coordinate pairs, or we could just list the x values. Let's look at another example. So in our second example, we have x squared equals 0. Again, I want to change this into a quadratic equation so I can graph it. So we're going to graph instead y equals x squared. So we're replacing the 0 back with the y equals. When we go to graph this, let's plug in some points. And we actually graphed this in our last video. This was our most simplified form. I'm going to start with 0. If we sub in 0 into x squared, I get 0 squared, but that's going to be equal to 0. So the first point on my graph then is actually already an x-intercept. I have 0, 0. So that's finding me one answer. Let's see if we have any more. So I'm going to plug in +1. When we plug in +1, 1 squared gives me 1, so we're at 1, 1. So I wouldn't find any more to the right, because again, since my A value here is bigger than 0, this graph is going to be facing upwards. So let's sub in some negative values. When I sub in -1, -1 squared is also going to give me +1. So I'm at -1, 1. From here then, I can start to see this U shape that's forming. So this is curving up and to the right. Let's make sure it goes through the point there. So curving up and to the right, there we go, and then up and to the left. Since the graph is a U shape and it's facing upwards, it can never turn back around and come back down. So my only x-intercept is going to be at 0, 0. What that tells me in terms of solving this equation is that my solution then, I only get one solution this time, and it's at x equals 0, since that is the only x value where I cross the x-axis. Let's look at our third example. Example 3 says x squared plus 2 equals 0. Again, to graph this guy, we're going to instead look at y equals x squared plus 2. So I'm going to draw my t-chart. I am keeping in mind what direction this parabola is facing. Is this graph going to open up or is it going to open down? So this graph is going to open up since our A value is still a positive value. So this graph is opening up. Why don't you guys plug in some points and then we'll check those points together. Okay, I'm going to start by subbing in 0. When we sub in 0, we get 0 squared plus 2. So I end up with +2. So if we go to start graphing these then, I'm at 0, 2. Now I know this graph is facing up, but there is still a chance that I could have an x-intercept if maybe this point is on one of the sides of the parabola. Let's plug in more points to find out. If we plug in 1, we get 1 squared plus 2, which will give us 3. Not plus 3, it will equal 3. So I have the point 1, 3 then. So this is definitely curving on the right side. Let's plug in some negative values to fully see what's happening. If I plug in -1, -1 squared is +1, then 1 plus 2 gives us 3 again. What that means then, our graph is facing up. I have what appears to be my vertex at 0, 2, and then a graph that is completely facing up from here. So in this case, it's kind of different. I don't have any x-intercepts because there's no way for this graph to turn back around. So I have no x-intercepts. What would be my answer then if I don't have any x-intercepts? Well, since our solutions are our x-intercepts, if I don't have any x-intercepts, then I have no solutions for this. So there will be graphs that if they're above the x-axis and facing upward, they'll never cross the x-axis, so I have no what we call real solutions. And when you guys take an Algebra 2 course, you're going to talk about numbers that are not real numbers, and that will kind of enlighten there. So I'm leaving this as a cliffhanger for your Algebra 2 class. If we have a graph that's facing downward, if it's below the x-axis and facing downward, then that would also have no real solution since it cannot cross the x-axis. In these first 3 examples, the reason we would want to solve them by graphing is because they're not too bad to graph. Let's look at example 4. So example 4 definitely looks messier here. My first vote might not be to graph it, but our instructions for this section do say to graph this one, so we can still go ahead and do it. It's just going to require a little bit more work to see the shape. So we're going to be graphing y equals x squared minus 2x plus 1. All the same stuff still applies. I want to think about what direction this parabola would be facing. And since our a value is still positive 1, this graph is going to face upward. So that will help me when I'm starting to plot these to make sure I have enough points. And I'm going to just start with 0 again. It's the nicest number to sub in, and it really lets me see a little bit of this graph. When I sub in 0, we get 0 squared minus 2 times 0 plus 1. The first 2 terms go to 0, and we just end up with positive 1. Let's make sure we have enough space. There we go. I'm going to go ahead and plug in positive 1. That's another nice value. So we get 1 squared minus 2 times 1 plus 1. Simplifying this, we end up with 1 minus 2 plus 1, and that actually gives us 0. So let's start graphing what we have so far. So far I'm at 0, 1, and I have a point here. Then I also have a point at 1, 0. Well, the graph has to be facing upward, so maybe it dips down a little bit below and comes back, or maybe this 1, 0 is our vertex. It's hard to see. I know that any point to the left of 0, so any negative values, should be producing larger values, and let's test that theory. So if I sub in negative 1, we get negative 1 squared minus 2 times negative 1 plus 1. So we end up with 1 plus 2 plus 1, so we do end up with a larger value at 4. So negative 1, we are up here at 4. And the reason I had a good idea that any negative values would produce larger values was because my graph is opening upward. So now I need to see, well, what's happening at 2? Does this graph dip below, or does it stay above the x-axis? So let's plug in positive 2. We'll get 2 squared minus 2 times 2 plus 1. That gives us 4 minus 4 plus 1, so we end up at positive 1. So at 2, we're up here at positive 1. What that's telling me then is since my graph is facing upward, this keeps curving up to the right, and it keeps curving up to the left, since we already do have 2 points on there as well. That graph is a little messy, it doesn't like touch the x-axis again, it curves up, there we go. And then, and up from there. So what this tells us then is that we have one x-intercept, and that x-intercept happens to be at 1, 0. So this is similar to example 2 where we only had one x-intercept. Oops, I forgot the word 1. So only one x-intercept up here as well. That one just happened to be at 0, 0. This one has been moved or shifted to the right, and it's at 1, 0. So our solution then for example 4 is just going to be x equals 1. So although example 4 looked a little bit more complicated to start with, we were able to graph it fairly easily. It just took a couple more points there to really see the shape. So it's important to keep in mind what direction this is facing so that you have a good idea of if you have enough points or not. Let's look at our last example by graphing. We have x squared minus 4 equals 0. Why don't you guys pause the video and graph this one on your own first. So we're graphing y equals x squared minus 4, and then we'll check it together. Okay, as we go to check this, I'm going to start off with 0. Gives me a good sense of the graph. So if I sub in 0, you get 0 squared minus 4, so we're at negative 4. So I'm going to start graphing this. So we're down way here at negative 4. Let's plug in 1. When we plug in 1, we get 1 squared minus 4. Well, that's going to give us negative 3. If we plug in negative 1, let's see what happens. We get negative 1 squared minus 4. That also gives us negative 3, since negative 1 squared is positive 1. So I know my graph is facing upright, since my a value is positive, so it is facing upwards. So this graph will intersect the x-axis. It has to keep going up. My job, though, is to figure out, well, where it does. Well, the best way to do that is just keep trying integer values. So let's sub in 2. If we sub in 2, we get 2 squared minus 4. Well, 2 squared is 4, so 4 minus 4 gives us 0. So we actually found one of those x-intercepts. Using symmetry, we actually know that the other x-intercept would have to be at negative 2, 4. And if we want to double check that using arithmetic, we can. Negative 2 squared minus 4 is equal to 4 minus 4, which gives us 0. Again, I can use that axis of symmetry, though, to really see that that point would be there. If we were to graph this now, we can see this graph will keep climbing up to the left and up to the right. Whoops. There we go. So I have 2 x-intercepts for this graph. I have an x-intercept at 2, 0, and an x-intercept at negative 2, 0. What that tells me then for my solutions is since our x-intercepts are our solutions, then my solutions here will be x equals 2 and x equals negative 2. Now, personally for me, graphing wouldn't be the first route I would try, just because it is more time consuming than other routes, but it's important to understand the connection on our solutions to our graph. And the biggest thing about graphing is that our x-intercepts on our graph are actually solutions to the matching equation. Because our x-intercepts are, of course, where we set this y value equal to 0. So when we set our y value here equal to 0, that's how we would solve for our x-intercepts, which also give us our solutions to that corresponding equation. Let's look at our second method for solving square roots, or for solving quadratic equations, which will be using square roots. So the key thing about square roots, and I said this way back at the beginning, was that the b term has to equal 0. This has to be true, otherwise square roots will not work. The reason being is I don't want the x term. So in our standard equation of ax squared plus bx plus c, this middle term of this bx I don't want to be there, and the only way to do that is to have b equal to 0. The next thing to keep in mind is our goal is going to be to isolate the x squared term and get that x squared all by itself before we apply any square roots. So let's look at our first example. We have 3x squared minus 75 equals 0. To get x squared by itself, I'm going to add 75. Then to finish off getting x squared by itself, if we divide through by 3, we can end up with x squared equals 25. Now here, to get x by itself, I can apply the square root to both sides. And we know from a past unit that the square root and the square cancel each other out, so I just get left with x. What I do have to keep in mind, though, is that this actually produces 2 solutions. Plus or minus the square root, then, of 25 is what we end up with for x. Now, in terms of reducing, if you can reduce the square root at all, if it's a perfect square, reduce it, or if there's values inside of it that are perfect squares, we're going to want to go ahead and reduce it. In this case, the square root of 25 is a perfect square, so we end up with x equals plus or minus 5 then as our final answer. And if we've never seen this sign, this plus or minus sign, so this plus and then the minus underneath means plus or minus, That's what that stands for. And it's representing the fact that x equals 5 and x equals -5. So it is representing both answers in there. You can either write it as one plus or minus sign, or you can write them as two separate answers, whatever you prefer. Why don't you guys pause the video and try example 7 on your own first. Okay, in example 7, our goal is to get x squared by itself. So I'm going to subtract 16. So we end up with 4x squared equals 0. Dividing through by 4, I get 0 over 4. Well, 0 over 4 is one of those okay scenarios because I have 0 on top over a non-zero number on the bottom. So this will be equal to 0. Now that I have the x squared term isolated, I can go ahead and apply the square root to both sides, remembering to have the plus or minus on the side without the x. The square and the square root cancel, so we end up with just x equals on the left side, and then we get plus or minus the square root of 0. Well, the square root of 0 is 0, since 0 times 0 is itself. So I end up with x equals plus or minus 0. Now, that looks a little funky to me because there isn't a difference between positive 0 or negative 0, so we're just going to write our final answer as x equals 0. So just like we saw in the graphing, we had some answers that gave us 2 answers, some that gave us 1, and some where we actually got no solution. That's still going to be true as we solve using other methods because they're all quadratic equations. So in our example 6 here, we ended up getting 2 solutions. In example 7, we actually only have 1 solution now. Why don't you guys pause the video and try example 8 on your own first. To check example 8, our first goal is to isolate x squared. So let's subtract 27 to the other side, divide through by 3, and we get x squared equals -9. Now from here, I would take the square root of both sides to get x by itself, and I'd get x equals plus or minus the square root of -9. Well, what is the square root of -9? The square root of -9 is not a real number because I cannot take square roots of negative numbers and actually get real numbers back. So since we're only finding the real solutions, in this case then, I have no real solutions. Oops. And that is because I cannot take the square root of a negative number and get a real answer out. Okay, we have 2 examples left for this video. Why don't you guys pause the video and solve both example 9 and example 10 on your own first. Let's look at example 9. So in example 9, I'm going to isolate x squared. So let's add 24 over. So we have 2x squared equals 24. Dividing through by 2, we get x squared equals 12. I'm going to square root both sides. And it's okay to do this because as long as I do to one side as I do to the other, I'm still keeping my equation balanced. Don't want to forget that plus or minus though. The square root and the square cancel, and we end up with x equals plus or minus the square root of 12. Now from here, the square root of 12 is not a perfect square, so it's not going to reduce completely, but it can reduce a little bit further. And in these cases, we want to just make sure we've reduced our answer as much as possible. So if we want to think about 12 on the side here, 12 factors is 4 times 3, and we know that 4 is a perfect square. So I can simplify this and rewrite this as x equals plus or minus the square root of 4 times 3. Since 4 is a perfect square and the square root of 4 equals 2, then we end up with plus or minus 2 times the square root of 3. That will be our final answer in example 9. Now I know I said to pause the video already to try example 10, but if you haven't, or if you maybe didn't simplify your answer all the way in example 10, why don't you pause the video and finish that off. To check example 10, I'm going to guess that you guys added 40 to both sides first. So we get 4x squared equals 80. Dividing through by 4, we get x squared equals 20. If we square root both sides, we can get x by itself, and we end up with x equals plus or minus the square root of 20. Now, similar to 9, the square root of 20 is not a perfect square, but there are perfect squares inside of it. So 20 factors as 4 times 5, and so I can rewrite this as x equals plus or minus the square root of 4 times 5. Since 4 is a perfect square and the square root of 4 is equal to 2, then we end up with plus or minus 2 square root of 5. That will be our final answer for example 10. So in this video, we learned how to solve quadratic equations by graphing and finding their x-intercepts, or by using square roots. And again, I just want to remind us that square roots only work if our b term is equal to 0, and that is key. And because this only works for square roots if our b term equals 0, that's why we have other methods to solve. And in our later videos, we're going to learn about a couple more methods in solving quadratic equations.